Practice exam 3, part 5. We're up to part C, validity and invalidity. 3 questions. Again, your real exam would be just like this. A proof, a theorem, prove a theorem, and a model universe method to show that something's invalid. Okay, so the first one is our proof. This is question 17. All right, so I've got my 2 premises at the top, conclusion at the bottom, as always. Take note of the kind of question it is, right? Is it a pure quantifier problem, like question 2 in the exercises from Unit 15, where the formulas are all either in quantifier form, 2 conditions of being in quantifier form, formula begins with a quantifier, scope of the initial quantifier goes all the way to the end of the formula. So if it's in pure quantifier form if all the formulas are either in quantifier form or are a CQN away from being in quantifier form, right? So here it's not in pure quantifier form, this one, but this, because we have a negation in the second premise, but the first one is a universal statement, conclusion is in quantifier form, first premise and conclusion both in quantifier form, both in fact A categoricals. This one, if we do a CQN, right, as we will do, first thing we do, it will be in quantifier form. That counts as a pure quantifier problem. It's distinguished from problems where the premises or conclusion have one or more formulas which are truth functional combinations of quantifier formulas, right? So where you've got a conditional or a conjunction, right? They're like the Unit 15 exercises question 4 problems, right? And those ones you have to be put in mind of the rules for modus ponens and modus tollens and so on, right? You cannot instantiate from or generalize to formulas that are not in quantifier form. It's the big point of Unit 14. All right, so this one, that's what you should note first. Is it pure or is it a mixed quantifier problem? Secondly, you're going to translate all the negated ones. We've identified it as a pure problem. All the ones which are negations, we're going to translate by CQN. So let's do that straight away. So what is this? That's a O form, right? It's a particular exclusion, negation here, so it's from nego. Is it E or O? It would be E if it was a universal quantifier, right? Nego, E, O, but it's a existential quantifier. So it's particular exclusion, so it's a not O, that's form, that goes to A, right? A goes with O, E goes with I. So, right, not A goes to O, not O goes to A, not E goes to I, not I goes to E. So this is equivalent to, should be this, right? There does not exist an X such that X is both G and not H. There does not exist an X such that X is both G and not H. There is nothing which is both G and not H. So all the G's are H. Yes, those are equivalent. For all X, if X is G, then X is H. What am I doing here? I'm reading back these symbols into English, reading these symbols back into English, these symbols back into English, making sure the results are logically equivalent formulas. In English, they ring, in my mind, as meaning the same thing, and they do. Okay, so that's correct. So that's that. So now what do we have? You don't have to cross this out or anything, but you're sort of, in your mind, ignoring this one now, right? All the information that was in there is now in here, right? So we're just working with 1 and 3. We're going to do something with them. We're going to instantiate them. But where are we heading? Remember the mantra for proofs, remain conclusion driven. Can't see it, but I'm standing on 1 foot. Remain conclusion driven, right? Look at your conclusion. What does that mean? Look at your conclusion, determine what form it is, think about, determine 2 things. What rule am I going to use to get a formula of this form? And what formula am I going to need to be able to apply this rule, right? How am I going to get this? So what is this? This is a universal statement, right? It is in fact an A categorical, but most importantly, it's a universal statement, begins with a quantifier, scope of the quantifier goes to the end, and that scopify is a universal. So I'm going to have to get this rule by what? By universal generalization. Since it's in quantifier form, it's probably going to be the case that the generalization rules, well, think like this. It's in quantifier form, therefore, the generalization rules are available. It has to be in quantifier form for you to be able to get it by a universal generalization, by a UG, right? And that is probably how I'm going to get it. And what I'm going to, that's pretty surely, since this is a pure quantifier problem, right, that's going to be the rule I need to use to get this. Okay, what kind of rule is UG, right? Now you're going to think it through. Remember, derive from its name, from the lectures, from recalling what I said in the lectures, derive from its name what kind of rule this is and whether this is a hard rule, that is a flag rule, a rule requiring restrictions and rules that teach you how to obey those restrictions. What kind of rule is UG? It's universal generalization. That means going from some particular instance and saying that it's true of the particular instance or the particular individual, say A, you're inferring from that to it's true of all individuals. Right? That's what universal generalization is. Generalization is going from an individual to a quantified statement where the propositional function true of the individual is true of one existential generalization or all universal generalization. Wait, from one to all? Oh, that's definitely a dodgy inference, at least in all circumstances, right? That is what universal generalization is, but clearly it's going to require some restricting such that it's truth-preserving as in the way that we use it, right? We always want inferences to be absolutely, perfectly preserving truth in all cases. So this is so UG. What I've determined is that's the hard rule, the hardest of the hard rule, right? The other hard rule is what? Existential instantiation, right? EI, if you think about what that means. There exists an X such that Fx it's true of Andrew, that Andrew is F, right? Or think about it like this. Somebody trampled my strawberry patch, therefore you trampled my strawberry patch. Is that a valid inference? No, not always. That requires restricting. That's why existential instantiation requires, when you write EI, you have to write flag A, right? But that's the easier of the two hard rules. The two hard rules are existential instantiation and universal generalization. You can deduce that from thinking through what the rule tells you you're allowed to do. But this is, of those two hard rules, EI and UG, UG is the hardest of the hard rule because before you do any instantiations up here, what do you do with UG? You have to set up the flagging subproof before you do any instantiations. You have to set up the flagging subproof before you do any instantiations because otherwise, when you do the instantiations, you will not be obeying the rules of flagging, which are that the flag letter has to be new to the proof. It cannot have appeared previously, right? And if you instantiate to, say, the letter A with this information, you're only allowed to infer from this propositional function, fx hook hx, that's a propositional function, you're only able to infer from that being true of the individual A to that being true of everything if you derive that particular propositional function being true of some individual within a quarantined subproof, which is what a flagging subproof is, right? Flag A. Flagging step for UG. Now, recall from the lectures, remember that universal generalization has the advantage that conditional proof has over indirect proof, right? Those are the two rules involving assumptions. Conditional proof, remember we saw a conditional down the bottom. To get that, we would assume the antecedent, derive the consequent, and that would allow us to infer the conditional. So when we set up, right, working backwards, remaining conclusion driven, we have the conditional, we put the antecedent at the top, and we put the consequent down the bottom of the subproof, because that's the specific formula now, which when we arrive at it, right, that's the specific formula we are aiming at as we do our proof, such that we know that when we get to that, that's the end of the subproof, and we're done. And then we discharge the assumption, move out of the subproof, back onto the main line, where we have derived our conditional, citing the rule of conditional proof. Similar advantage, indirect proof didn't have that. Indirect proof, you assume P to derive not P, but you don't know exactly what particular formula is going to allow you to end the subproof. You just know that it has the form Q and not Q, whenever you have some contradiction, but you don't know what particular contradiction. Whereas conditional proof, it had the specific formula, namely the consequent of the conditional you're trying to derive. Similarly here, right, make sure when you're setting up for UG, you write the flag A up here, and you write the specific formula down here, right, from which you will be doing the generalization. How do we get this? It's just the opposite of instantiation. What is instantiation? Deleting the quantifier, replacing all the instances of that matching quantifier with some letter, the letter to which you're instantiating. This is not instantiating, this is sort of the opposite of instantiating is generalizing. But this is me determining what formula I need to arrive at to do the generalization, right? So if this was a premise, all F's are H, and I was instantiating from it, I would go from this formula to this formula. Universal instantiation, A for X, A/X, right? Because generalization is the opposite of instantiation in determining what formula should go here that I need to aim at and arrive at to complete my subproof. That's what I get. F, right? The variable's gone away, the quantifier's gone away, all the variable X are replaced with A's. That's the thing I need. This is a conditional, and you could continue to work back and set up a conditional proof, and you get home that way. In fact, that would be a very easy way to do it. FA and A, and then FA, HA. Do your universal instantiations. Your one or two modus ponens is away from home, but you actually don't need to. It's not necessary on this one. But that's all the hard part. Now, you just universally instantiate twice. Flagging step is 4. 5 and 6 are FA hook GA and GA hook HA. That's UI on 1, UI on 3, right? So you have instantiated, delete the quantifier, replace the variable with the same individual constant. UI, think about what it says. Propositional function is true of everything, so therefore it's true of the individual A. Yeah, that always holds, so no restrictions. Universal instantiation is an unrestricted rule. It doesn't matter that the A has been flagged, it's still, the things which are true of everything are still true of the quarantined individual A, so don't be shy about universal instantiating to the same individual that you flagged. So the whole point is that you're allowed to do that. The whole point of this flagging restrictions. And then, if you can see, 5 and 6 are, you can do HS 5, 6. That's it, right? Hypothetical syllogism from these two, 5 and 6, and then UG on 7. Notice that we say just the last step, 7, different from conditional proof and indirect proof, where we cite the wholesome proof. Just the last step we cite.